All right, so I'm back with part 2 of our cardiac cycle diagrams. And we went over this one earlier, which is diagram in a different book that I have used. And now we'll fill out the one that is from your book. And they just flipped it. It's the same cardiac cycle diagrams, but we'll go through this. And so let's start with the pictures since they have that first. Again, this is early diastole. And so you have active filling here. And when I say active, you have filling of the ventricles, but the active part is right here. This is the P wave, which is atrial contraction. Right, so the atria are contracting after depolarization. So this follows, the SA node traveling to the AV node, and you have this P wave during that electrical activity, which then follows contraction, so atria contraction. And at that point, the atria contract, and remember, this is pressure. We have it here, pressure, right? And so this is ventricular pressure, and this is atrial. And so the point at which ventricular pressure exceeds atrial pressure, right there, that is where the AV valves close. And that follows this period right here, which is isovolumetric contraction. All valves are closed, but the ventricle wall is starting to contract there. And that is following, this is the QRS complex. This, by the way, is the P wave. And here's your first heart sound. And that is the AV valves closing. So this is all happening, right? So AV valves close. At this point, this is the volume of blood in the ventricle. That volume is now staying the same because all valves are closed. And so what you're seeing here is AV valves. And this is semilunar. And these are closed. And these are open. And here's where they're all closed. And here at this point, where ventricular pressure exceeds aortic pressure, because again, this is aortic pressure. This is atrial. I lost the screen for a second. Let's see if we can bring it back. There we go. Atrial, and then the green here is right, so those are the pressures. Sure. And so here is where semilunar valves are going to be open, and here's where the AV valves are going to be closed. Blood at this point is getting ejected out of the heart, so the volume drops in the ventricle. It drops from here to, whoops, I didn't do that very well. Drops from here to here. This up here is your end diastolic volume, and this down here is your end systolic volume, and this drop in volume that's being ejected is referred to as your stroke volume. That is the volume of blood ejected from ventricle during one cardiac cycle. And how do we find that again? It's end diastolic volume minus end systolic volume, and that's going to equal stroke volume. All right. Now, as the blood ejects here, This is systole. Gosh, can't spell today. Systole. Blood is ejecting, right? Ejection. Ventricle. When enough blood ejects from the ventricle pressure or ventricular pressure drops below aortic pressure, and this triggers the, this is semilunars open, and here's the point where semilunar valves close. Okay, so semilunar valves close here, and this here is, you've got all valves closed, all valves are closed. And so this would be your end systolic volume. This, by the way, the volume in here is your end diastolic volume. And so this period right here is called the isovolumetric relaxation period, or you're actually, this volume right here, I'm doing a very good job. So that's isovolumetric relaxation. There's a continuum of drop here in the ventricular pressure, and at the end of isovolumetric relaxation, it ends because the AV valves open, because the ventricular pressure now drops below aortic pressure, or atrial pressure, excuse me. And that triggers the AV valves to open. And here now you have early diastole. And again, diastole. And you have ventricular filling going on again. And so again, here you're going to see the volume start to go back up because you have venous return. And blood is returning back to the heart and filling the ventricles with blood. Again, this here is a second heart sound because semilunar valves close. And this coincides with the T wave, where you have, oops, ventricular, let's come back, where you have ventricular relaxation. So this is where you have the beginning of diastole, and this is where ventricles are filling here. And then that would mark a P wave, and you would start the cardiac cycle all over again. So AV valves at this point open, semilunar valves close, and you have one cardiac cycle. And so these diagrams really are tying together everything that's going on in the cardiac cycle. Now, in a kind of a more meaningful way is talking about when you're dealing with someone and you want to know if they're in heart failure. What we generally look at is their heart rate, stroke volume, and what that is to their cardiac output and what it is to their ejection fraction. And ejection fraction is the amount of blood pumped from ventricle or out of ventricle. So amount of blood volume pumped out of the ventricle as a percentage of what was actually available to pump out. Right, so it's a percentage. So what this actually means is you look at stroke volume, which is how much is pumped out, divided by end diastolic volume, which is how much you had, right? So amount available and the amount actually ejected, right? So it's the amount ejected divided by how much you have available, and obviously you multiply it by 100 to get a percentage, right? And that's your ejection fraction. You're looking at how functional your heart is, right? Because you have a certain amount of blood available, how much is actually being ejected. And you could do this by looking in like a hospital setting. You could see if they have a cardiac cycle of 0.6 seconds, what would their heart rate be? Well, remember, heart rate is beats per minute, right? And one cardiac cycle equals one beat, right? One heartbeat. So you have one heartbeat, that's one cardiac cycle. So if it's happening every 0.6 seconds, so this is happening every 0.6 seconds. Well, how many seconds are in a minute? 1 minute is going to have 60 seconds. So you can say 1 minute is equal to 60 seconds. And then you ask, how many 0.6 seconds can we get in 60 seconds? And another way to do that is to say, okay, let's divide 0.6 into 60, right? So how many, we can say, right? How many times can we get 0.6 into 60? Because if we have a heartbeat every 0.6 and it's 60 seconds in a minute, how many 0.6s are we getting? How many cardiac cycles are we getting? And this is just, you move the decimal place over and you have to add a 0 here. And 6 goes into 6 one time and then 0, 0. So you have 100 beats per minute. So the answer is heart rate's 100 beats per minute. It's a tad bit high, I would say. It's on the quote normal spectrum. In my opinion, it would be a little bit high, but still considered normal. Stroke volume, it's telling you the end diastolic volume is 110, right? So it's end diastolic volume minus end systolic volume. That's what stroke volume is. And so end diastolic volume is 110 minus 65. And so if we subtract 65, we get 5 and 4, we get 45 mLs. Now that is a really low, stroke volume. A good stroke volume would be 65, 70 milliliters. And if you recall from lecture, a normal cardiac output is going to be about 5 liters per minute, or 5,000 milliliters per minute. And so if you multiply, because remember cardiac output is equal to heart rate times stroke volume. And in this case, it's 100 times 45. I hope you can do the math in your head. And so that is 45,000 milliliters per minute, or 4.5 liters per minute. And that is a low stroke volume because normal is about 5 or a little bit higher. So what does that mean for their ejection fraction? Again, ejection fraction is equal to stroke volume, how much was ejected, divided by how much was available. And we know the stroke volume now is 45 mLs, and diastolic volume was 110 mLs. And so if we do the math there, and you multiply or divide 45 by 110, you're going to end up with 40.9. Well, it's actually 0.409, but then you multiply by 100 and you get 40.9%, or you can round up to 41%. So the ejection fraction here is 41%. Is this person healthy? Absolutely not. Normal ejection fraction should be greater than 50%. 41 is definitely not greater than 50%. This person is in heart failure, not a good sign. And so this concludes this worksheet.